So we were discussing about strain gauge, which is extensively used for measurement of strain or force, or we'll see pressure and many other variables. And the strain gauge, the resistance is given as Rg is equal to R0 into 1 plus G into epsilon, where G is the gauge factor. We know this is basically delta R by R divided by delta L. And this we have already seen that the gauge factor depends on the extensively on the material, and we have got different materials and different gauge factor we have it. And also we have seen that this strain gauges have to be connected. Actually, best way for connection of the strain gauge and take out the output voltage signal out of it is basically connecting it at a bridge. So suppose I put them in a bridge and denote R1, R2, R3, R4 as the 4 strain gauges we are connecting. And we have seen that for temperature compensation, because the strain gauge resistance may change with temperature, for the temperature compensation, we better to always use 2 or 4 active strain gauges. 2 or 4 active strain gauges. So they are to be connected in that way that the adjacent arms should be experiencing the opposite strains, and the opposite arms should be experiencing the same strain like this. So in this way we have the perfect temperature compensation, and also because of the 4 strain gauges put together we get more sensitivity. And we have already seen that E0 is equal to this E, and if we say the bridge arm ratio is equal to A, I call it, then it is EA divided by 1 plus A whole square into G1 epsilon 1 minus G2 epsilon 2 plus G3 epsilon 3 plus of G4 epsilon 4. So this is an approximate expression, but quite accurate at the same time, because the strain normally applied is very small and change in resistance is always less than 1%. So it is always linear, and if it is linear we can approximate it. So what we have is that all the 4 strain gauges, they may be experiencing different strains, and they may be also in general say suppose they are experiencing, they have got different gauge factor G1, G2, G3 and G4. So this is the finally we can get an expression if we recall, it is easy to remember and we can find it out. And also if A is equal to 1 and G1 is equal to G2 is equal to G3 is equal to G4 is equal to say G. That means all of them are identical strain gauges, active strain gauges, which gauge factor equal to 4. Then we can express it as equal to E0 is equal to E by 4 into G into epsilon 1 minus epsilon 2 plus epsilon 3 minus epsilon 4. So this is the way we can calculate the unbalanced voltage there. So for example, we can say a cantilever for measurement of the force. If we apply a force here and say suppose we place two strain gauges, one at the bottom and one at the top at the near the fixed end. So if it is so, this one will be under tension, the top one, and the bottom one will be compression. Here it would be minus epsilon. And this case, what we can say actually this cantilever, the expression is strain at fixed end is epsilon is equal to 6 F into L divided by Y B T square. What is that? L is the length, B is the width, and T is the thickness, while Y is the Young's modulus of this one. So in this case, I can, looking at it, I can straight away say that E0 is equal to E into G divided by 4, and here it would be into, we are fixing only two active strain gauges. So naturally, the other two strain gauges, so suppose I can say R3, R4 are fixed. So I can easily calculate that this will be Eg by 2 epsilon, Eg epsilon divided by 2. On the other hand, this is one way. On the other hand, if I had, instead of this one, so suppose I put a on the top itself, this is the configuration 2. I put it like this is your 1 and this is your 2 there. So I put 1 at the top and 1 at the top itself, but it is in the perpendicular. In that case, what is the configuration 2? Because often it is difficult to access the bottom surface of this one. So in that case, for configuration 2, what we will write is that E0 is equal to Eg by 4 into 1. What it would be? Because it is epsilon minus epsilon in the earlier case, and here it would be, what is the strain it is experiencing? Minus epsilon into, mu into epsilon, where mu is the Poisson's ratio. That we know it. So it would be 1 plus mu into epsilon. So it is, we can, so with this formula, we can always write it E0 is equal to Eg by 4 into 1 plus mu. And also, we'll come to it afterwards, the load cell and etc. etc. But we can calculate different configurations. So for this example, we have seen that cantilever, we can have both one at the top, one at the bottom, or two strain gauges, one and both of them on the top, but one is along the axis and another is perpendicular 90 degree to it, and we can get exactly this one. And we have also expressed that zero adjustment last day, where we have showed that the zero adjustment because the strain gauges may not be exactly the same values. So for that one, and with a variation of less than 1 ohm, it is always better. And to put a parallel resistance which is RZ1, which is in the range of 25K or like this approximately, in series with another fixed resistance RZ2, and we call it, this is a zero adjustment. And second thing also, we had mentioned that for the sensitivity adjustment, because the battery may go down or like this, we need to calibrate this one often. So what we require is put another potentiometer here, which we call it the sensitivity adjustment. So these are often required, this one. And also we have mentioned in the last class that we need to have a calibration. That means in the laboratory you can generate, because that strain generation is difficult unless strain generation is always difficult in the laboratory, because we will have to generate this much force and this is the area there. So while you calibrate in the laboratory or do it like this, we put a parallel resistance RC in one of the arm. So here it is RC is a calibration resistance. Okay. So this is a thing we have already come across and do the things there. Now we go for the applications of it. So the applications are different. It could be force measurement, it could be pressure measurement, it could be torque measurement, all of them. But ultimately, the basics configurations are the same. That is, there are multiple number of strain gauges and multiple number of, and they are connected in a different way, and a bridge configuration. So for the force measurement, we have already one cantilever that we have already expressed this one. And also we can have a what we call it load cell, that is for weighing. Actually what you are doing is primarily in a shop or like this, what are the weighing machines are there. They are primarily this sort of load cell where they have the weight is placed on suppose some sort of base, a block, maybe where at the center the force is applied, and we can have 4 strain gauges. So it would be like this. 1, 2, 3, 4. In that case, there would be perfect temperature compensation. And second thing is that maximum sensitivity. So you know that 2 and 4 will be under compression and tension, while 1 and 3 would be under compression. So here also we can easily say what will be the value of E0. From these expressions we can say it is equal to, from the last expression, E into G, because there are 4 gauges, while there were 2 gauges here, and they are satisfying all the things there. Here it is, so it is 2 into 1 plus mu we are telling, into epsilon. So this is the case we have it, because here is by 4 strain gauges, and this is possibly the formula you had used in your measurement lab while carrying out the experiment. But before going further, but my question is that, okay, I think this I can remove, because all of them are the same there. My question is that, will there be perfect temperature compensation? What do you think? Apparently, definitely all the strain gauges are identical. They have got the same material. So, there would be the strain gauge will be perfectly temperature compensation. But if we recall the expression for the cantilever, we have seen that this is equal to epsilon is equal to 6FL divided by YBT square. The problem is that Young's modulus Y decreases with temperature. So naturally, what would be if the temperature increases, definitely the bridge will not be affected, all the things there, but because of the decrease in the Young's modulus, the generated strain will be more. It will be showing more strain. Naturally, if we calibrate and do the things there in terms of force, so it will be showing more force if the temperature increases. So what could be the way out? Can you suggest? What could be the way out for this one? Because we need to compensate for the decrease in Y with the temperature. I tell you answer. This is for that one. We modify slightly the circuit by putting some RTD. We have studied already. That is an RTD in series. Why and how? Basically, as the temperature increases, Young's modulus will decrease, as well as that the strain indicated will be more, but the RTD resistance will also increase. If the RTD resistance increasing, that effectively the voltage received by the bridge is reduced. If the RTD resistance increases, so basically effectively the voltage received by the bridge will decrease, and as a result the apparent change in increase in the epsilon or the strain can be made compensated by using an RTD, and obviously we need to properly design the RTD material, resistance and all the things. But definitely this can be done nicely often for the force calculations, and also we'll see it for pressure or temperature and all the things. But for the time being, while you go further, we'll assume that these temperature compensations have already been taken care of. So we will go for the other applications of the strain gauge. So the third application is interesting, often for measurement of force, that is called, because it has got these strain gauges, have got several applications in mechanical engineering. That's called, one of them is proving ring for the force measurement, because often we require force measurement in different orientation, different area, and often if we say, suppose if we want to measure tensile strain, how do tensile force, because this load cell can give you a compressive force, but the tensile force it cannot measure. For this one, what we do is that we use some this is your proving ring. And basically, if you look at it, at this end, we have some threads at the two ends. And we apply force at this. And we place 4 strain gauges in this manner. One is outside the ring. That means we just paste it on that ring there, and one inside the ring, inside surface of the ring. So I call them 1, 2, then it is 3, and this is 4. And this is, suppose the resistance is R, the radius is R and the thickness is T. Okay. Now can you tell me what would be the direction of strain? Which one would be positive strain? Which one would be the negative strain? Yes, I require your answer and suggestions. What my question is that 1, 2, 3, 4. Among this 1, 2, 3, 4, definitely all of them are not under tension, or all of them are not under compression. Some of them under tension, some of them under compression. What is, and we are applying a tensile force here. So what would be the direction of strain? Anybody? Anybody? Saurabh Mishra, what is your opinion?
Sir, I think, sir, 1 and 4 will be in tension.
1 and 4 will be tension. 1 and 4?
No, sir. 2 and 3.
Huh?
2 and 3.
4. And?
And the rest 2 would be in compression.
Wrong. Anybody? Anybody else? This is not the case, because rather the case will be just the opposite. If we look into, just you put it your hand like this there. your palm, you just fold it like this, bend it like this. Once you try to move it up, what will happen? Inside edge will be trying to expand, while the outside edge, it is trying to contract, because there would be wrinkle on this side there. So inside edge is getting a positive strain, while the outside edge will be actually getting a negative strain. So that is interesting. Often I also thought that initially that this should be the area, but actually the 1 and 4 will be, 1 and 3 will be under tension, and 2 and 4 will be under compression, but they will be the same strain they would be experiencing like this. And this epsilon is given by, if radius is much higher than the thickness T, there is a mechanical, I am just using this formula from the mechanical books and etc., is equal to 1.08 F into R divided by Y dt square. So anyway, so we can place the 4 strain gauges in this way and pull these two things on both the two sides, and we can get a strain generated, and from that one you can, after measuring the strain, I can get back what is the force here. Okay. Next is that so this is the third one, that is the proving ring. Torque measurement. This is the torque measurement. You know, this torque measurement is one of the most difficult measurements actually, because often for a motor or like this, what is the torque generated, what is the torque transmitted, and we know that is the actual torque or the mechanical torque. It is difficult always, because often we say that, okay, P is equal to twice pi nt or like this, but what is the exact mechanical torque we do not know, because there are certain, any rotating body, frictional loss, with windage loss and all the things there we cannot calculate. So, but we want actually, there is a shaft, suppose there, and one end is a driving a motor, and maybe the other end is driven by a pump or any other thing, rotating body like this. Okay. So I write it down that this is your length of this shaft, and suppose I provide this part, I just fix it and I make it, I apply torque here. So what will be the result of it? What would be the result of it? You can easily understand that if we, for the sake of simplicity, I assume that one end is fixed, I hold it, and one end I twist it. So in that case, there would be, I am just showing you in a very enhanced area, there would be some twist. And this angle is known as phi, that is a twist angle. And this one, the twist angle is related to the phi by, twist angle is related to this one by the expression, okay, by the expression phi by t is equal to 2L divided by pi into Gs into r to the power 4, where r is the radius of this one. R is the radius and Gs is called the shear modulus of elasticity. But that does not help us, okay, I understand this one, but that does not help us for finding out and how to applying the strain gauges and how to apply strain gauge there. So, but one thing is clear, that whenever there is some torque applied and there is some twist there, so naturally there would be some, because of the twist or because of the shear force, there would be some strain would be developed. And our objective is that in which direction, what is the strain is positive or negative, and which direction it is maximum, and all that like this. So it can be shown that, just I am showing you. This is your axis. So suppose I put it the torque in these directions and so that there is a torque in this. The maximum strain, it can be shown, occurs at 45 degrees. So if I draw a line of 45 degree here and obviously another line of 45 degree here, and we place two strain gauges like this. This is one. This is one and this is two. So you can see there from the air, the one will try to elongate. This is a plus epsilon there, and while two will try to compress. This is given a minus epsilon. And this one, the maximum strain is epsilon is given by 2t divided by pi Gs into r to the power q. So naturally, this is the way we can mount two strain gauges in this shaft, or even we can mount four strain gauges, say along this 245 degree, where the strain developed is the maximum, and then we can find out what is the strain there. But there is a problem there, obviously. What is the problem? If we recall the strain gauges, say suppose I consider all the four strain gauges. So all the 4 strain gauges, another 2 I must put it, they will form a bridge there. And along the shaft, I would be, this whole, the strain gauges all would be rotating. But what we require is that at least 2 arrangements. One is for battery connections and one is for, okay, I put it here. And one is for voltage measurement. And definitely the voltage battery should be mounted on a static one, and the voltage I want to measure, that has to be amplified, and all these things will be in the static area. But the sensor, which we are showing it, is rotating continuously. Now the question is that how would you overcome these situations, and how would you transmit the signal from the battery to the strain gauge, as well as get an unbalanced voltage and get it amplified by some static amplifier or a voltmeter. So what we call it is that transmission of power or like this. So what we can do is that in that case, one way is that what we can do is that the strain gauge bridge may be there. Now I place 2 copper or gold plated rings are there. And rather we require 4 rings or like this, but I am showing you for the sake of simplicity 2 only. So these are called slip rings. These are called slip rings. That means this will be some sort of using some brush or this one spring arrangement. There will be a static EA there, which will be always making a contact with the ring here, and this will be the connecting ring here, and similarly for the other, all the 4 there. So that there I can get the transmit the power, and I can get this voltage and all other things like this. Am I clear? If I am clear, then possibly you can easily understand what is the difficulty. Another, the problem is that generation of noise due to wear and tear.
Hello, sir.
Yes.
So can you explain again this arrangement?
Huh?
Like the arrangement which you drew, the slip rings. Can you explain it again?
Okay. The shaft you understand which is rotating? Over
Yes.
the shaft, I place 2 rings. Actually, there are 4. I am just showing the 2 rings there. And this one is touching. This is a static brush or like this there. This is a static carbon brush like this, which can provide you the electrical contact. So if the static brush is that it's fixed over here and it is always touching, then there would be always some electrical signal we can transmit. You can transmit. If you recall in your, I think, school days and nowadays DC motor, whether it is taught or not, I don't know, where the DC motors also, we use the similar type of brush to collect current or pass the current. The similar type of thing, it will be touching this part, and naturally then the battery you can connect the supply here, and similarly another two for the getting thing. So basically these are two copper rings, so it is rings, and this and these are basically brush, you can say it. So they will hold and they will touch this with the spring one, so that they can push current and take out the current from it. So this problem can be solved, but the problem is that often this brass has to be held tightly with this one, and with regular use there might be wear and tear and like this there, and maybe if there is any eccentricity of the shaft, then there may be always some constant jerking type of signal, you will get it. So naturally that will generate some noise. This voltage will not be on a continuous DC, but maybe always some DC superimposed by some noise or like this, and which is not very convenient and which is not very desirable. So naturally, this is the thing. Is it clear now?
Yes, sir.
So now this is the thing there, and there may be other methods also which we are not elaborating because we are not elaborating, but there are other methods. But all the cases, I will say that among the different types of measurement, the torque measurement is one of the most difficult measurement for instrumentation. It is easy to say, okay, this is the amount of torque, but this is the torque area. But measuring it online and like this, there will be always some noise and there would be some problem. Often what they do can be done is that instead of giving a DC battery or like this, we could use some AC, because strain gauge can be used for AC circuits as well. We can use some transformer. Instead of this one, we could use some transformer, so that this one and this one, this is one winding of the transformer, this is another winding of the transformer. So they can couple, magnetically couple and transmit the signal. That way also there. But these are always, you can say, there are certain pros and cons or some hazards associated. But torque measurement is always difficult. One way of doing it is slip ring, there are other methods. We are not, you can go through some books or literature and go for it. Okay. Now, lastly, I will go for pressure measurement. You know, this is another important issue of pressure measurement is that, say, suppose we call it a diaphragm. Suppose one end we apply some pressure P there. And what will happen? When the diaphragm must be very thin and like this, if the diaphragm is thin and the material is soft enough, what will happen? There would be some deflation of the diaphragm. There would be some deflation of the diaphragm. Now, what will be, if there is some deflation in the diaphragm, so naturally I can measure by the deflection of the midpoint here. This is one way we can do it. Or we can also use strain gauges, because using the strain gauge we can, because due to this pressure there would be some strain developed in the diaphragm, and by properly choosing the placing the strain gauges and doing, we can do the we, we can measure the strain and also comparatively the diaphragm. So that can be done if we take, say, suppose it's a circular diaphragm. You can see it at the center. If I place it on the top of it, two pressure strain gauges, say suppose 1 and 3. Okay? So I can say that this is, I place it two strain gauges. Here it is 1 and this is 3. Both of them will experience what is that? They will experience some strain, positive strain, because this is deflected, it is elongated, so diaphragm is elongated. So naturally we are getting a positive strain. On the other hand, if I place another two strain gauges, I will show it afterwards, maybe while discussing more details about the pressure transducers, I will discuss this one. What will be happening is that in this case, there would be 2 and 4. They both of them, what they will experience? They will experience a compressive force if it is put on this side. So I can say it is, this one is plus, so I can say that this is 1, 2, and this is another 2, 4 there. And I can say that they will experience some compressive stress, but that may not be exactly the same. So if it is epsilon here, it is a minus epsilon 1 here. So these things, the details of this compressive force, what would be the A, I will discuss it afterwards on this one. So we can have a diaphragm type strain gauge. In fact, we can have some sort of diaphragm type rosette. We have told it already. Diaphragm type rosettes there, we can make it. I will show you those things while I discuss more in detail about the pressure. But we can say that force strain manner, we can generate some voltage where it is the voltage pressure there. Okay. So I stop here. If you have any question, you can ask me for 2 minutes or like this, because we have already more or less, we have given some strain gauge, explained some strain gauges. We will give you some problems within a day or two on strain gauge, and after that we will slowly move to some other type of resistive. There are many other resistive type transducers, but I don't think want to confine in one type of resistive, in all types of resistive transducer only. Rather, we like to give exposure of different types of other types of transducers, and possibly we can understand they are on the same principle. If they are, the principle is same, you can, the working and etc. It is not very difficult to understand. Okay, thank you.